in our previous sessions, and we have seen how to execute this counters, this and all things we have seen in our previous session. So everything will be uploaded in the same channel. The recordings will be uploaded, but it will take some time, like 2 to 3 days of time it will take for uploading, but it will be uploaded. So this is what we have started our discussion. We have started with the discussion of how to design your mod 4 counter and mod 8 counter and mod 16 counter we have seen. And also we haven't discussed about mod 3, mod 5 and mod 9 yet. And we need to discuss this f by 2, f by 4, f by 8, f by 3 and this frequency divisions using these counters. And we are still discussing about the synchronous counters. Now, in our previous session, we have started with your mod 4 counter design, where we have seen how to design this counter, everything we have seen, and how to design your mod 8 counter and how to design your mod 16 counter we have seen. And about this mod 8 counter we have learned, and we have actually tried to design a model which is going to behave as a mod 2 counter, mod 4 counter, mod 8 counter and mod 16 counter. Depending upon your mode signal, it is going to behave. That particular design we have seen in our previous session, and the links are also posted in the group. You can check it out. So this and all things we have discussed in our previous sessions. Now in this particular session, we are going to discuss about frequency division using counters. So first of all, we will try to discuss frequency by 2 using counters. Okay. So in our digital design also, if you have watched those particular videos, we have discussed what do you mean by frequency division by 2 and how to achieve this frequency division by 2. We have seen in our lectures in digital design. You can watch in the playlist. So we will try to implement that particular thing using Verilog. Now, how your frequency division by 2 is going to look like. So let's say this is your clock. This is your clock pulse. It is going to look like this. Now, and we are going to have an output which is our frequency division by 2. So what do you mean by frequency division by 2? So it will become 1 here, and up to this cycle it will become 1 and it is 0. 1, 0. So let's say this is your time period T clock and this is your output time period T out. So you can see the relation T out is equal to 2 times T clock. You can see, right? And this is nothing but T out is equal to 2 times T clock, and my output frequency is nothing but 1 by 2 times of F clock. If I reciprocal, I will get my output frequency, which is nothing but my clock frequency by 2. So this is your waveform. This is how your waveform is going to look like. And how to get our frequency division by 2? Simple circuit we can take. We can take a simple T flip-flop, and you can connect simply input as 1 and connect a clock, and this is your output, which is nothing but my f by 2. Okay, or else you can also have a mod 2 counter. You can simply have a mod 2 counter for getting your frequency division by 2. This we have already discussed in our previous sessions. Now your mod 2 counter is going to count from 0 0 0 1. Sorry, so your mod 2 counter is only going to have only one bit. So it is going to have the count sequence like 0, 1, next 0, next 1, next 0. Okay. So this is how your mod 2 counter is going to look like. Now, if I want to implement this in my Verilog, how to implement, let us see. So before that, we will see frequency division by 4 also, and we will go to the implementation part. Now, in the case of your frequency division by 4 in digital design lectures, we have already seen that how to implement your f by 4. We will simply take a mod 4 counter. We will simply take a mod 4 counter for implementing this. Your mod 4 counter sequence is going to look like it is going to take 2 bits 0 0, 0 1, 1 0 and 1 1. Okay, this is your sequence. Now I will write it vertically 0 0, 0 1, 1 0 and 1 1. This is your LSB bit and this is your MSB bit. If you consider this MSB bit, this is nothing but your frequency division by 4. Okay. How it is frequency division by 4? This also we have already had a discussion. Let me once again show it to you. Let's say this is your clock. And if I plot this particular MSB, then it is simply 0 for one cycle, 0 for two cycles, and 1 and 1, and again it is 0, so on. If I consider the time period, this is my T clock. From one rising edge to another rising edge, it is 1 T clock time period, and here this is my time period of my output, T out. So if I find out the relation, T out is equal to 1, 2, 3, 4, 4 times of T clock. If I convert it into frequency, my F out is equal to 1 by 4 times of F clock. So for getting my frequency division by 4, I should consider a mod 4 counter. And similarly for frequency division by 8, if I want to achieve a frequency division by 8, I am going to take a mod 8 counter. I am going to consider a mod 8 counter where the counting sequence will be 000, 001, so on to 111. And if I consider the MSB bit, I am going to get a frequency division by 8, 010, 011, 100, so on 111. If I consider this MSB bit, then here I am going to get a frequency division by 8. Okay. During digital design, when we were discussing about counters also, I've shown you. Now, so this we need to implement this with our Verilog coding. Now, so what I'm going to do is I'm going to first of all open the tool. Yes. So let us create a file next, and create file. So let's say it is frequency by 2, frequency divided by 2 circuit, and press simply OK and finish. So your source will be created. Let us wait for the creation of this particular file. Press yes. So if you are not aware of this tool interface, the Vivado tool interface, everything, please rewatch the recordings which are available in the playlist. In the initial few sessions, we have discussed about this particular things. Once revisit them. So where is this frequency division by 2? Yeah, frequency divided by 2 circuit. Let us open this. So first of all, let us see the block diagram of how your frequency division by 2 is going to look like. So this is your block, which is going to have a reference clock and a reset signal, and your output is nothing but F by 2. This we need to design it. Okay. So how to design it? I'm going to write it down. Let me zoom in a little bit. So input is my clock and reset, and I have output as F by 2. This is my output. Let me take it in reg. Okay. So if I always iterate passage of clock, if I apply my reset signal, input clock comma reset, output F underscore 2. Yeah. No semicolon. Yeah. If reset, then my output will become 0, and I'm going to use a non-blocking assignment. So why to use non-blocking assignment, everything we have discussed, and simply I'm going to write down F by 2 is equal to not of F by 2. So what is going to happen, let us see, and followed by always begin and followed by end. Okay, so this is nothing but your frequency by 2. So what you're going to do initially, this value, so initially this value will be equal to 0, and next passage of clock, and next passage of clock, if it is occurring, then it will be toggled and it is becoming 1, next 0, next 1, next 0. This is nothing but my mod 2 counter or frequency division by 2. Okay, so let us write down the test bench for this and let us check it out. So this is my design, and go to sources and press on this plus, create simulation source. Yes. So I'm going to write down, first of all, I need to declare my inputs and outputs, reg clock comma reset, and wire F by 2. Okay. and I need to instantiate my design. So my design name I will copy here and paste it over here. DUT clock reset f by 2. These are my inputs and outputs. Excuse me. And let me initialize my variables. Initial my clock reset will be equal to 0 and end, and I'm going to generate a clock. Always #5 clock is equal to not of clock. So I'm going to generate a clock here. Now, so after generating the clock, I'm going to apply my reset signal. How to apply this reset signal? If reset, sorry, within an initial begin block, initial begin reset is equal to one tick binary 1 and #10 reset is equal to one tick binary 0. Okay, and followed by end, and followed by end module, which is already present. Yes, so this is my test bench. Let me save the test bench and the design. And after writing your code, make sure that your test bench is set as top so that it is only simulated. So let me make it as a top, set as top. And after that, press run simulation. So your design will be simulated. Let us check what is the output we are getting. Let us wait for a few seconds. Yes, so we are getting our output. Let us verify how your output is going to look like. So this is my clock. Let me zoom in a little bit. So this is my clock. This is my reference clock and this is my output. So if my clock is completing 2 cycles, then my output is only completing 1 cycle. This is nothing but my frequency division by 2. Okay, so your output time period is greater than your 2 times more than your reference clock. Okay, so this is how we can achieve our frequency division by 2. Okay, now let's say if I want to design a circuit which is going to perform frequency division by 4. So how to perform it? So for frequency division by 4, you can design a mod 4 counter. I need to design a mod 4 counter. How to design a mod 4 counter? In our yesterday's session only, we have seen how to design your mod 4 counter. Now, after designing this mod 4 counter is of 2 bits. Let's say Q1 and Q0. It is going to look like this: 0, 0, 0, 1, 1, 0, and 1, 1. I need to consider only the MSB and I should give it to the output and I will get F by 4. This is how I can design a mod frequency division by 4. Now let us check it out. So already we have the design which is present because we have already designed it in our yesterday session. Let us check it out. Yeah, this one, mod 4 counter. Let me open the file, and this is my mod 4 counter. This is Testbench. Let me open the design. Now here let me copy this entire thing and let me create one more file. Create design source f by 4 circuit and press OK and finish. And let me copy it. Yeah, so here I need to add one more. So this is my let me change the design name, f by 4. So in this f by 4 we have clock reset enable output reg 1 down to 0 count. Instead of this 1 down to 0 count, what I'm going to do is output f by 4. Okay, and internally I'm going to declare the counter reg 1 down to 0 count. Okay, and here what I'm going to do is, using the assign statement, assign f by 4 is equal to count of MSB. That's it. And let us write down a test bench for this also. So this is my f by 4 and let me save this. So is it clear? Any doubts or any queries in this f by 4 circuit? So I will copy the test bench of my mod 4 counter so that it will be easier. Where is my mod 4 counter? Okay, let me search it. Mod 4 counter. Yeah. Let me copy the test bench of my mod 4 counter and let me paste it in my f by 4 circuit. I need to change the design name and test bench name. F by 4 underscore TB is my test bench name, and my design name is F by 4. F by 4 underscore circuit. Okay, rest all is same, and I need to have the output as F by 4, and I need to declare it where F by 4. Okay, let me check it, cross verify. F by 4, the module name is F by 4. Yeah, and rest all is same. That's it. So let me save this and let us run this. And before that, make sure that your test bench is set to top, then only the correct file will be executing. Right click on it and click set as top. Yes, so where is my output? Here. So this is my F by, okay, it is still showing the previous one. F by 2 it is showing. Let us add the F by 4 also. So go to scope. Okay, okay, let me close the simulation. Still F by 2 frequency test bench is getting run. So I should make sure that my frequency division by 4 circuit module has been running. So what I will do is go to simulation and make it as a top and run the simulation again. Yes, so this is my F by 4. Let me show you. And count we are getting Z because it is unconnected, right? So we can just neglect it. And yeah. So this is my F by 4. Let me show you. And once I will modify the design, count is equal to count plus 1. Okay, I need to increase my enable 1 minute in the test bench. Let me make it as 100. Since your enable is made to 0 after 5 cycles, that's why your counting process has also been stopped. That's why we are not going to get any output. Let us make it as for 100 cycles. After 100 cycles, we will make our enable to 0, so that after 100 cycles, your count will be equal to 0. In our previous session, we have seen, right, this enable signal. Yeah. So this is your frequency division by 4 which we are getting. So this is your clock. So if your clock is completing 1, 2, 3, 4 cycles, your output is completing only 1 cycle. This is nothing but your frequency division by 4. And your counting process will be happen until and unless your enable is equal to 1. If your enable is equal to 0, your counting process will stop and your frequency division will also is also going to stop. Okay, so this is how you are going to design your frequency division by 4 and frequency division by 2. And if you want to develop your frequency division by 8, you can consider a mod 7, a mod 8 counter, and you can take down the MSB and you will get frequency division by 8. So any doubts or any queries in which is going to have clock, reset, and let's say enable signal, and one more thing is mode signal. This mode signal is of, let's say, 2 bits, and we have our outputs as F by 2, F by 4, and F by 8. Okay, so these are our outputs. Depending upon your mode signal, okay, we can take one more output also, F by 16. Depending upon your mode signal, if your mode is equal to 0, 0, you need to have frequency division by 2. And if your mode is equal to 0, 1, you need to have frequency division by 4. And if you have 1, 0, you need to have frequency division by 8. And if you have 1, 1, you need to have frequency division by 16. This is our requirement. So depending upon your mode signal, and whenever your enable is equal to 1 only, then your frequency divisions are going to happen. Okay. If your enable is equal to 0, your frequency division is not going to happen. And depending upon your mode signal, this particular operation should happen. Okay, so how to do this? Simple. So yesterday's session we have seen one design. Where is this design? Multiple frequency divisions we have seen. Let me open that. Universal latch SRCO. Yeah, multiple even up counters. This particular design I will open file. So this particular design is can able to count mod 2, mod 4, and mod 8, and as well as mod 16, this particular thing. So if it is equal to 0, 0, it is a mod 2 counter, and if it is equal to 0, 1, it is a mod 4 counter, and 10 it is a mod 8 counter, and 11 it is a mod 16 counter. In our yesterday session we have seen this. Now by taking this counter, we have only taken one counter, which is a 4-bit counter, which is going to count from 4 zeros to 4 ones. So your counter, internal counter, is going to count from 4 zeros to 4 ones. Like this it is going to count. Okay, 0 0 0 1 0 0 1 0 0 0 1 1 0 0 0 1 double 0 and so on. Okay, so what we are going to do, if we consider only this bits, if we consider only LSB bits, then we are going to get frequency division by 2. And if we consider the second position, okay, then you are going to get frequency division by 4. And if you consider this position, you are going to get frequency division by 8. And if we consider this position, we are going to get frequency division by 16. So we have seen this all in the counters also. When we have 4 D flip-flops like this, then from here we are going to get frequency division by 2, and from here we are going to get frequency division by 4, and from here we are going to get frequency division by 8 and frequency division by 60. Okay, so the same method we are going to apply in our coding also. How to apply this? Let me copy this entire code and let me create one more file. Create design source, multiple frequency dividers, and press OK. Paste it down here, and let me change the file name, multiple frequency dividers. So this is my design name, and here I'm going to change my outputs. So my output is reg f by 2 and output reg f by 4, output reg f by 8, and output reg f by 16. And here mode, and I will remove this up down signal. Yesterday's session we have seen this. And counter underscore internal. Okay, I will remove this down bar, this we don't need. Yeah, so here instead of your mod to count, I'm going to write down f by 2, f by 2, and here I'm going to write down f by 4, and I will take only index position 1, and here I'm going to consider f by 8. I'm going to consider index position 2, and I'm going to consider f by 16, and index position is 3, and this is your f by 2, f by 4, f by 8, and f by 16. So if you're not able to understand this once, watch the recordings when it get uploaded. So yesterday session we have started with this code development, which is a multiple frequency division, multiple counter generation. Okay, I'm using the same code, just a few changes. That's it. I'm considering the mode signal. So depending upon your mode signal, you are going to get that particular frequencies. Okay, and let me save this file. Create simulation source. Create file. Multiple frequency dividers testbench. Press OK and finish. And I will copy the same thing. Where is this multiple counter underscore even underscore tb? Let me open this, and I will paste it over here, and the file name is multiple frequency underscore tb. Clock reset enable mode. I don't need this signal, and this signal also I don't need this signals. I will add my signals wire frequency by 2, frequency by 4, and frequency by 8, and frequency by 16. These are my signals. Enable, I will remove this up down counter. So I will add those signals f by 2, f by 4, f by 8, and f by 16. These things I have added, and down bar is not present. Let me remove this. Yeah, that's it. And here also down bar is not there. Let me save this and let me keep the mode as 00 so that your frequency division by 2 should happen. Let us check. And before that, I need to make sure that you have correctly instantiated your design. So the design name is, let me copy the design name, multiple, where is my design? Yeah, this is my design. Let me copy the design name, multiple frequency dividers. Control C and paste it over here. Multiple frequency underscore TV. Let us make it as stop, set as stop. So before running your design, make sure that you have set as stop and run the simulation. So let us check what is your output which we are getting. So I've only added my frequency division by 4. Okay, first I need to close this simulation and let me run it one more time. Yes, so we will see what is your output which we are getting. So coming to your frequency by 2, yeah. So since your mode signal is equal to 00, we are only getting your frequency divided by 2. Let me show you how it is. Yeah, this is your frequency division by 2. Since your mode signal is equal to 00, your frequency by 2 is getting. If you apply mode signal is equal to 01, you will get frequency by 4 and accordingly frequency by 8 and frequency by 16. Let me show you frequency TB. Let me change it to 10 so that I will get frequency division by 8. Let me relaunch it. Yes, so this is my frequency division by 8 and why I'm not getting for long period because my enable is making and getting 0. Let me increase the enable time period so that I can see my entire waveforms, multiple frequency division underscore TB. Here I will view my enable signals for after 500 cycles I will make it to 0 so that I can see the entire waveform of my frequency division by 8. Yes, so this is my frequency division by 8 which I can see. Okay, so if your clock is completing 8 cycles, 1 2 3 4 5 6 7 8, your output is completing only 1 cycle. This is nothing but your frequency division by 8. So accordingly you can choose whatever frequency you need to have. Okay. Yes, actually this type of circuit is implemented in your FPGA also. So that's why we are also covering this so that if you, when we are discussing about the FPGA course, we can again recall the things which we have seen. Okay. Yes. So that's about your frequency division by 2, 4, 8, 16 and counter design, counter mod 2, mod 4, mod 8, mod 16. And in our next sessions, we will see everything odd like mod 3, mod 5, mod 7, mod 9 and frequency division by 3, 5, 7, 9. And if you are not confident about this particular concepts, I recommend you to once rewatch the sessions which are present in the digital design if you are not confident about the frequency division. And if you're not confident about the counter design, please rewatch the sessions when uploaded in the YouTube on the Verilog so that the things you will be in continuation. Okay. Yes. So that's about this particular session. If you have any doubts or any queries or anything you wanted to discuss with me, you can stay and discuss with me or else you can leave the session. Okay. Thank you.